Okay, we're starting chapter 4, which is forces between particles. Okay, you remember the noble gas configurations, and they have to do with this last column right here, which starts with helium, and they go all the way down to an octane. Remember what was special about them? How many valence electrons did they have? Do you remember? There was 8 valence electrons. There were 2 in the S and 6 more in the P to make up that S. So we're looking, remember, across the row like this. There was one exception to that rule, and that was the first shell. The first shell only has 2 valence electrons, but every other shell has 8. Now as we look at this, we learned something called Lewis dot, if you remember. Okay, remember Lewis dot, we took a symbol, any symbol, and we wrapped around like our orbital notation. We took the S, we took the first P, which is known as px, the second P, which is known as py, and the third P, and we wrapped it around it, pz. We wrapped it around it like that. Now, the periodic table, the valence shell electrons, the ones in the yellow and the red here, they have a specific Lewis dot for each family or column or group, especially the valence electrons. So we're going to look at the first column here. First column is going to have just one dot representing one valence electron. The second column is going to have 2 dots, one on each side, representing 2 valence electrons. I'm going to hopefully give myself enough room here. Boron's column over here, boron's column has 3 valence electrons, and their electrons are negative. They're going to go as far apart from each other as possible. So we have 3 in a triangle. Then we have carbon's column, where we get 4 valence electrons. And we have nitrogen's column, where we have 5 valence electrons. 2 on the top and 1 on each side. That didn't show very well, but that's what it is. We have oxygen's, where we have 2 on the top, then we put 1 in each of the P and go back in pair. Then we have fluorines, 1 in each of the P, go back in pair. We have one group that's not paired. And then we have the very last column right here, which is the noble gas column, which has 2 on each side. Represent 2 in the S, 2 in each of the P orbits. So they show you really quickly with the Lewis dot the valence shell electrons. Okay, so let's practice a little bit. I've got bismuth here circled in yellow on the periodic table. You should have your periodic table out so that you can use it a lot. We're going to start with a noble gas above bismuth, which is xenon. Remember, we play the Price is Right, closest to without going over, and that is xenon. So we're going to put, as a noble gas for bismuth, bismuth is going to be like xenon, put it in brackets, and we add on from there. So then we go over here to the 6s, and we add the 6s2. We go down to the 4f, add the 4f14, come back up to the 5d, and add the 5d10, and then we add 6p, 1, 2, 3. Now, remember that you can't leave it that way. Noble gas configuration says you have to rearrange it according to shell out, or how much you added each shell. So we'd rearrange that, and it would be Xe, 4F14, 5D10, 6S2, and 6P3. Now to do the Lewis dot for bismuth, I just write bismuth, Bi, the symbol, and I look and I say, look, there are 1, 2 S and 1, 2, 3 P to get there. So I put 2 in the S and 1 in each P. I'm done. Okay, say that I wanted to do something else, maybe bromine right here. So I would write bromine is equal to, which noble gas, remember the noble gases are the last column, is closest to without going over, remember the Price is Right, and it is argon. So we're going to put argon in brackets and say bromine is like argon, and then we start on row 4 and we write, but it has 4s2 and it has 3d10 and it has 4p 1, 2, 3, 4, 5. 4p5. Now remember to rearrange. So bromine is like argon, but in the 3D it has 10. In the 4s it has 2. In the 4p it has 5. Now, looking at this a little bit closer here, we remember for our Lewis dot we're going to have the 2 here and the 1, 2, 3, 4, 5 here. Notice we have 2 here and we have 5 here. So as we go to make bromine's Lewis dot, we're going to write bromine. We're going to put 2 in the S and 1, 2, 3, 4, 5 in the P. Now there's a whole bunch more problems that you can go through and check, and in your book it might not be a bad idea to go through those examples and see if you can do them. I'm going to go on to 4.2. Okay, in the ionic bonding we still need to remember the octet rule, which is that we want to get to 8. Remember, all the noble gases had 8. They had 2 in the S and they had 6 in the P to get their 8, which is the outer octet or the valence electrons. Now, they're either going to gain or lose electrons to be that way. So let's look at a couple of them. Let's look at Be. Be is right here. It has 2 electrons in its outer shell. So if we do the Lewis dot, it looks like this. Now, is Be closer to 8 or closer to 0? Well, if you said closer to 0, you're right. It's going to get rid of those 2 electrons to become like the noble gas neon below it. When it does that, because it's getting rid of 2 electrons that are negative, the protons in the center still are the same. So what happens is, if we write an equation for that, is beryllium will give up 2 electrons and become beryllium plus 2 as a charge. Because remember, it's neutral to start with because my electrons and my protons are the same. So they balance out and equal 0. But if I give off 2 electrons, which are negative, then I become positive. Let's pick another one here. Let's maybe go the other side here, bromine. So I'm going to change colors here just to keep us straight. So bromine, if we do the Lewis dot for bromine, it has 2 in the S and it has 1, 2, 3, 4, 5 in the P. Now, is it closer to 8 or is it closer to 0? Well, of course it's closer to 8. It wants to get one more right here and become like the noble gas krypton. So what we do is we write bromine wants to gain an electron, and therefore it will become bromine negative. Now remember, girls, I talked a little bit about this in class when we were looking at the charges and what they become, you know, and guys think about it too. If a girl loses weight, she is happy, she's very positive, but if she gains weight, she's very negative. Okay, so let's do just one more. Let's do geranium here, Ge. So here's Ge. Ge has 2 in the S and 1 in the P, but it's in carbon's column, which has 4 electrons, and we put them on each side. So here, which is it closer to 0 or is it closer to 8? Well, here's the conundrum. It could lose 4 electrons, or it could gain 4 electrons, just as easy. So it could become like the noble gas krypton by gaining electrons, or by like the noble gas argon by losing electrons. So we have 2 equations that we could do. If geranium is going to lose electrons, then we write it like this, and germanium becomes a +4. If germanium is going to gain electrons, we write it like this, and germanium becomes a -4. Now, from 1 to 3, it can only gain, or excuse me, it can only lose, because it hasn't opened up all the 4 orbits so that it can't get up to 8. After 4, it can gain or lose. Okay, it's probably easier for it to gain after the 4th column, because at the 5th column I'm closer to 8 than I am to 3, but it can do either or, so you can have either charges, so you've got to be careful there. You need to be able to write these equations like I've been writing them for any element in the S and the P, and be able to find out what's going on with it. Okay, so one other thing we want to talk about here, if I have, say, aluminum, and aluminum has 3 dots around it, is it going to gain or lose? Well, it's probably going to lose, right? So we have aluminum, and it's going to lose 3 electrons and become aluminum +3. This is known as an atom. An atom has a neutral charge, or no charge. This right here is known as an ion. It has a charge. Now, if the ion has a positive charge, it's known as a cation. If an ion has a negative charge, it's known as an anion. Okay, so let's look at one more equation here. Let's take oxygen. Oxygen has 2 in the S and 1, 2, 3, 4 in the P. So is it going to gain or lose? Well, most likely it's going to gain. If you said gain, that's right. It is going to gain. So if oxygen gains 2 electrons, it becomes O2-, meaning, or O-2. It can be written either way depending on who you talk to. Now, that makes it isoelectronic with the noble gas, what? Well, the noble gas that it becomes when it gains 2 electrons, or becomes like, is neon. So neon has the same number of electrons in this outer shell as O2-, from O-2. And that is known as isoelectronic. So if I'm asking you to tell me what noble gas is isoelectronic with, or if I'm telling you if I have N-3, what noble gas is it isoelectronic with? Well, let's look. N-3 is going to be isoelectronic with what? Do your best, see if you can figure it out. If you said neon again, you are right. Okay, so real easy to figure out. What happens though if I'm now going to subtract? Okay, what element then, or what noble gas would be isoelectronic with Al +3? It is also neon, because I have given up 3 and become like the noble gas below it. Alright, that's it for 4.1 and 4.2. We'll see you at 4.3.